Lesson 9.4, Velocity and Acceleration of Vector Functions. I noticed that it said in this final lesson, this is not the final lesson, so I'm going to take that out. We can use the concepts of vector-valued functions and parametric equations to study the motion of an object along a curve. As a particle moves along a curve in the plane, let's define the position vector r of t using the horizontal movement x equals x of t and the vertical movement y equals y of t as functions of time. By doing this, we will use the derivatives of r of t in order to describe velocity and acceleration of the object. So definitions of position, velocity, acceleration, and distance. Given that x of t and y of t are twice differentiable functions of t, the position function, I keep saying function, I'm sorry, the position vector of a particle is r of t equals x of t I plus y of t j. The velocity vector, acceleration vector, and speed at time t are stated below. So based on that r of t, your velocity, which is going to be the derivative of r, is going to be the derivative of x of t times I plus the derivative of y of t times j. Our speed, which we put the double bars around the v to denote speed, is going to be the square root of x prime of t squared plus y prime of t squared. And then the acceleration would be the second derivative of r of t, and it's going to be x double prime of ti plus y double prime of tj. And then the distance would be the integral from a to b, from t equals a to t equals b, of that square root of x prime of t squared plus y prime of t squared. So now, the derivative as a tangent vector. The derivative vector r prime of t points in the direction that is tangent to the path traced by the position vector. So we know that the limit as delta t goes to 0 of delta r over delta t is equal to the limit as delta t goes to 0 of r of t plus delta t minus r of t divided by delta t. That's like the definition of a derivative. So as delta t goes to 0, delta r over delta t approaches the velocity vector as shown in the figure at the right. Velocity and acceleration are vectors that have both direction and magnitude. And so let's look at example number 1. Find a rectangular equation that describes the object's motion. And by the way, I don't know if you want me to say anything about this picture right here before we start going, but notice that you've got, some function moving along this, some particle. Let's imagine that it's a particle moving along this function right here. And to get to this point, like this is a point on your r of t, it has a vector here, which is a culmination of the x vector plus the y vector, right? And then you can go to this other point, going to that point, and again, x vector, y vector, or you can go directly to that point, x vector, y plus y vector, xi plus yj. So now, let's go down here to our example number 1. An object moves along the plane curve C described by r of t equals 3 cosine ti plus 2 sine tj. And Part A, find a rectangular equation that describes the object's motion. So what I would do is I would look at this and I would say, well, I know that my x is my 3 cosine t, and I know that my y is my 2 sine t, and so I would try to solve this so that cosine is by itself, solve this so that sine is by itself. If you remember, for parametric equations, the next step for this would be to square both sides. That would be our next step, because we're trying to produce something that we can use a trig identity on. So this gives us x squared over 9 equals cosine squared t, and y squared over 4 equals sine squared t. Now if we add these together, we would be adding our left-hand sides. Oops, that's a 4. It almost looks like a 9. And we would be adding our right-hand sides. And that's when we see the Pythagorean identity here. So since we see that Pythagorean identity right here, and we know that's equal to 1, then our equation becomes x squared over 9 plus y squared over 4 equals 1. That is your rectangular equation for this problem in example number 1. X squared over 9 plus y squared over 4 equals 1. Part B, find the velocity vector, speed, and the acceleration vector. All right, so our velocity is going to be the derivative of r. So we say the derivative of 3 cosine t is going to be negative 3 sine t times I. And the derivative of 2 sine t is going to be 2 cosine t times j. So there's your velocity vector. So that right there is velocity. Our speed, which is, like I said, our double bar r. I'm sorry, our double bar v is also double bar r prime. And when you see that double bar, you need to be thinking of Pythagorean theorem. So that's why we're doing square root of our x squared plus our y squared of our velocity vector. So this gives us the square root of 9 sine squared t plus 4 cosine squared t. And since you can't really do anything else with that, you're done. That is your speed. Depending on what your t value is, that will find your speed. And the last one was acceleration, which we said was the second derivative of position. And so we're going to take the derivative of velocity here. So the derivative of 3 sine t, I'm sorry, negative 3 sine t is going to be negative 3 cosine t times I. And derivative of positive 2 cosine t is negative 2 sine t times j. And that's your acceleration vector. And so now, for part C, it wants us to sketch a graph of the path and use arrows to show direction. Now, what I did on this is I'm going to make this smaller. I made a chart, I made a T, X, Y chart. And since we were talking about sine and cosine, I just went from 0 to pi over 2 to pi to 3 pi over 2 and then back to 2 pi. I just did that because it was sine and cosine was in our x and y. And using the position function, which is our 3 cosine ti plus 2 sine tj, I put t equals 0 in, so 3 cosine of 0 for x is just 3 times 1, which is 3. And then 2 sine of 0 is going to be just 0. So that's going to be your starting point. I would think that your t is, it's moving along, and at some point you say, okay, we're going to start here. Pi over 2, we've got 3 cosine of pi over 2, which is 3 times 0, which is 0. 2 sine of pi over 2, which is 2 times 1, which is 2. 3 cosine of pi is 3 times negative 1, which is negative 3. And then 2 sine of pi is 0. And then 3 cosine of 3 pi over 2 is 0. And 2 sine of 3 pi over 2 is negative 2. And then 2 pi, you're going to have that same thing that you had at 0. Okay, so it looks like we're going from 3, 0 to 0, 2. And we always put a little angle to show, or a little arrow to show which way we're going. And then from there we go to negative 3, 0. So that means that we're traveling like this. I'm going to make my arrow again. And from there we go to 0, negative 2. So that means we're traveling like this. And from there we go back to our 3, 0. And so that's the path of the particle. And it wants us to show the vectors use arrows to show the direction. Okay, we did that. They want us to show the velocity and acceleration vectors at the point 3, 0. So what we're going to do is we're going to say our v of t at t equals 0, because that 3, 0 is right here, and that's at t equals 0, right? So this is our point 3, 0. What t value is it at? If they wanted us to find it at negative 3, 0, we'd be using pi for t. But they said 3, 0, so we're going to use 0 for t, okay? And so our v of 0 then is going to be negative 3 times the sine of 0 I plus 2 times the cosine of 0 j. So this is actually going to be 0I plus 2j. So it's just 2j. So to show that you are on this point, you don't go anywhere x, y, left, right, but you do go 2 up. So from this point, I would just go like that, and that would be our velocity vector at 0. And then our acceleration at 0, we've got negative 3 cosine of 0 times I plus negative 2 sine of 0 times j. So this is negative 3I, but then 0j. So this is just negative 3I. So for our acceleration vector, from this point 3, 0, we're going to go negative 3, meaning left 3, and then don't go anywhere for j. So this right here is our a of 0. So there's our velocity and acceleration vector at that point. Okay, so now example number 2. Sketch the path of a particle moving along the plane curve by r of t equals 4 minus t squared I plus tj. Then find the velocity and acceleration vectors at t equals 1. Sketch them on the graph. Okay, so they want us to sketch the path of the particle. So the first thing I would do is make a chart. And I guess I'll go ahead and make my chart t right here, x, y, And you can see that, well, we always basically start at 0. And I'm just going to go, 0, 1, 2, 3, 4. I don't know. So now, my r of t, you can see that my x is going to be 4 minus t squared. So 4 minus 0 squared is 4. My y is just t. So my y is 0. My x at t equals 1 is going to be 4 minus 1 squared, which would be 3. And my y is just 1. And then for x equals 2, or I'm sorry, for t equals 2, my x would be 0. My y would be 2. For t equals 3, my x would be 4 minus 9, which is negative 5. And my y would be 3, because my y is just t. And then 4 minus 4 squared is 4 minus 16, which is a negative 12. And this would be 4. So I don't know if I'm going to be able to plot all of these, but I definitely can plot the 4, 0, the 3, 1, the 0, 2, the negative 5, 3, and I think I have to stop there, but you can see at least that this is what your function's doing. Put some of those arrows in there so that we can see the direction of the movement. And that is sketching the path of the particle, okay? That's the path of the particle. Then they want us to find the velocity and acceleration, okay? So our velocity function is going to be the derivative of this r. So the derivative of my x is going to be negative 2ti, and the derivative of my y is going to be 1j. So that is my velocity function. They did want my velocity function at 1. So negative 2i plus j. I only had one place to put the t equals 1 in. And then my acceleration function is just going to be negative 2i, because when I take the derivative of 1j, I get 0j. So my acceleration function is just negative 2i, and my acceleration then at 1 would just be negative 2i again, because I don't really have a t to put the 1 in. And if you wanted to practice, oh, it does say sketch them on the graph. Okay. So they want us to sketch them. At t equals 1, your point is 3, 1. So this is going to be where you're sketching them from. Okay, sketching the vector, the v of 1 and the a of 1. So v of 1 is going to be negative 2 to the left, positive 1 up. And so I started at 3, 1. I went negative 2, positive 1. So I'm going to try and draw that vector. Oh, I didn't draw it very straight, but that's my v of 1. And then my a of 1 is just going to be negative 2i, so it's just going to be negative 2 this way. That's my a of 1. Okay, on to our next one. Example number 3, the position of a particle at time t is given by r of t equals 2t cubed plus 3t squared I plus t squared minus 12tj. Write an equation for the line that is tangent to the path of the particle at the point where t equals 1. Okay, so for this one, I kind of numbered them. I'm like, okay, the first thing that we need to do is we need to find out what r of 1 is, right? And so if I put r of 1 in, I would get 2 plus 3i plus 1 minus 12j. And then that simplifies to 5I minus 11j. So if I wanted to talk about what my r of 1 is, I could also write it like this with the vector symbol as 5 comma negative 11. And then the second thing I need to find out is I need to figure out what my v of t is. So I'm going to take the derivative here, 6t squared plus 6t times I plus, then we have 2t minus 12 times j. And then our v of 1 is going to be 6 plus 6 times I, so that'd be 12I. And then 2 minus 12j, so that'd be a negative 10j. And again, if you want to, you could write it as, you know, a vector, or just leave it like this. I'm okay with that. So now, the dy dx is the third thing we're going to find. Okay, our dy dx. Change in y over change in x. And so our change in y over change in x for our velocity is going to be negative 10 over 12, which is negative 5/6. And then the last part, part 4, would just be taking that slope and that point. So y equals negative 5/6 times x minus, now remember, you want your position at 1. So this is going to be x minus 5 and then minus 11, because you're using this right here. That's like your point, and this is your slope. And so we used the point and the slope to write point slope. So there's the equation of the line tangent to the path of the particle at the point where t equals 1. All right. So find the coordinates of each point where the horizontal component of the velocity is 0. So horizontal component, here's horizontal. And so that component, and by the way, assume that t is greater than or equal to 0. So the horizontal component is going to be your 2t, because remember, the x is the one where you go left or right. 2t cubed plus 3t squared. That one is your horizontal component. So we are going to look at its derivative, dx dt. So that's 6t squared plus 6t, and we're going to set it equal to 0. And I notice right away that 6t can be factored out, and that gives me t equals 0, t equals negative 1. We can throw out negative 1 because we don't have negative time. So the coordinates of the point where the horizontal component of the velocity is 0, okay? So we're talking about where t equals 0, so we're going to find r of 0, because we want to know what's happening there. So when we go back to our r, it looks like it will be 0I and plus 0j. So really, this r of 0 is just your 0, 0 vector, which is the origin, okay? So therefore, at the origin, v of t equals 0. And then example number 4, given a of t equals negative cosine ti minus sine tj, and v of 0 is 2I, r of 0 equals j, find the position vector. Then find the position at time t equals 3. Well, they gave us the acceleration. So if we integrate acceleration, we would have velocity. So our velocity function should be that integration. So let's think about that. What would the integration for negative cosine t be? That would be negative sine t plus some constant. We're going to call that the constant 1 times I. And then what about negative sine? So if I integrated negative sine, that would be positive cosine. So plus cosine t plus some other constant, that's going to be constant 2 times j. So that is your velocity, okay? They told us that our velocity at 0 is 2I. So what we're going to do is we're going to say, well, since v of 0 equals 2I, then I know that my negative sine t plus c1 has to be 2. So c1 has to be 2 plus the sine of 0. I should have put 0 there. So my c1 is just 2. And then since we know that it's a 0j, we could also say that our cosine at 0 plus c2 is 0 because it's 0j at t equals 0. Because if it just says 2I, we know that that's also meaning it's plus 0j. So this would be 1 plus c2 equals 0, so c2 is negative 1. So now I can give, based on this little piece of information, I can give my actual velocity, which would be negative sine t plus 2I plus cosine t minus 1j. I just put in 2 for C1 and negative 1 for C2 and got my correct velocity function for this, because it gave us that initial condition, right? Once it gives you that initial condition, it goes from being a family of functions. This is a family of functions. It goes from being a family of functions to a particular solution. This is the particular solution based on that initial condition. And now, if we want to define the position vector, we just need to integrate our velocity vector. So now our r of t is equal to, so if I wanted to take the derivative and get negative sign, that would be positive cosine, and then plus 2t I. If I wanted to take the derivative of sine, I would get cosine minus t. Uh-oh, guess what I forgot? I forgot my c. Sorry. I'm going to call this C3 I plus, this was sine t minus t plus C4 j. Okay, so now they gave us that r of 0 is just 1j. Okay, it's j, so that's 1j. That means that it's 0I plus 1j. So I can say that the cosine at 0 plus 2 times 0 plus C3 is equal to 0 because it's 0i. So that's 1 plus C3 is 0, so C3 is negative 1. And I can say that the sine 0 minus 0 plus C4 is equal to 1 because it's 1j. So that's C4 is equal to 1. So now I can give my R of t, because this was a family of functions until we got the initial condition. And now we're going to write the particular solution. With our C3 in and our C4 in. So cosine t plus 2t minus 1i plus sine t minus t plus 1j. And now they want the position, which I'm going to do in a different color, position at 3, at t equals 3. And so this is going to be the cosine of 3 plus 6 minus 1 I, sine 3 minus 3 plus 1j. So cosine 3 plus 5i plus sine of 3 minus 2j. And if you put that in your calculator, your R of 3, it would give you 4.010i minus 1. Oops, sorry. I don't think it liked me writing there. 859j. So that is your position at t equals 3, okay? Which is another thing that they asked for on that problem. But boy, we gave them a lot, didn't we? This was our ending velocity function. This was our ending position function, and then we had the position at t equals 3. Okay? All right. One more page. So in pre-calculus, we solve vertical motion problems using the position function subject to gravity. S of t equals negative 1/2 g t squared plus v sub 0 t plus s sub 0, v naught plus s naught, where s naught is the initial position, v naught is the initial velocity, and g is the gravitational constant of acceleration due to gravity. We use either 32 feet per second squared or 9.81 meters per second squared. So a projectile with mass m launched from an initial position r naught and having an initial velocity v naught has a position vector of r of t equals negative 1/2 gt squared j plus t v sub 0 plus r sub 0. Likewise, the path of a projectile launched from an initial height h and an angle of elevation theta, neglecting any air resistance, is described by the vector function r of t equals v sub 0 times the cosine of theta times t I plus negative 1/2 g t squared plus v sub 0 sine theta times t plus h j. And so your x is going to be your initial velocity, that's like your initial speed times the cosine of theta. Y is the initial speed times the sine of theta. So that kind of gives us an idea of how this is going to work with our projectile motion problems when we have vectors. So for example number 5, and I can't remember, I just wrote here that this would be like your x would be your v sub 0 cosine theta times t, and then your y would be negative 1/2 gt squared plus v sub 0 times the sine of theta times t plus h. So, you can see it, that it's what's being multiplied by j, that is the y value. What's being multiplied by I is going to be your x value. But just showing you that, those are still what we're thinking there. So example number 5, at a recent Civil War reenactment, a cannon charge was fired from ground level at a 60-degree angle of elevation and an initial speed of 300 feet per second. Find the following. They want us to find parametric equation for the cannonball's trajectory. So it told us that our v of 0 was 300 feet per second. And it also said that it was fired from the ground, so our r of 0 is 0. But the acceleration, if we sketch this, because you're talking about a 60-degree angle here, right? And I'm just going to drop, put a point on there and drop a perpendicular. This is going to be square root of 3, 1, that's going to be 2. If we just put our vector in, and we know that it will be coming down, being pulled down by gravity at negative 32 feet per second squared. And that would be the up-down movement of j. So that's going to be negative 32j. And so our x is going to be, so that initial velocity times the cosine of theta times t. So our x is going to be 300 times the cosine of 60 times t, which gives us 150t, because cosine here would be 1/2. So that would be 150t. And our y value is going to be, our height from the ground is 0. So if we did height first, that would be 0. And then if we did the v sub 0, that's 300 times the sine of 60 degrees times t, and then minus our 1/2 times 32 times t squared. So this y is going to give us 300 times the square root of 3 over 2, which is going to be 150 times the square root of 3t minus 16t squared. So there's your y and your x. So our parametric equations x equals 150t, y equals 150 times the square root of 3t minus 16t squared. Those are our parametric equations, which is what they asked for in that part A. Okay, the maximum height reached by the cannonball, you're going to want to figure out that, that up-down y value. You're going to find your dy dt, set it equal to 0. So dy dt is going to be 150 times the square root of 3 minus 32t. And that's what we want to set equal to 0. So 150 times the square root of 3 equals 32t. Divide by 32 on both sides. And that's going to give us 75 root 3 over 16. So that's the time. That's not the height, right? That's the time when it's going to reach its maximum height. So now you've got to figure out what y of 75 root 3 over 16 is. So if you look at your y and you're putting in, you've got your 150 times the square root of 3, you're putting in your 75 times the square root of 3 over 16, and then minus 16 times the 75 root 3 over 16 squared. I'm going to continue this down here. So when I look at this, I say, well, I can definitely divide 150 and 16 by 2. And I can simplify this a little bit also, because square root of 3 times square root of 3 is 3. So this is going to become 16,875 over 8 minus, now I need to square all of this. So when I do that, I end up with 16,875 over 16. So if I wanted to add these, I'd have to multiply by 2 so that they would both have the same denominator of 16. And that would give me, when I subtracted, after I multiplied this one by 2 and subtracted this one, I would end up with 16,875 over 16, which is approximately 1,054.688, and this would be feet. So that's the maximum height. Went up over 1,000 feet. And then for part C, the horizontal distance traveled by the cannonball. So for that one, our y is 0, but we're going to set our x equal to 0, which our x was our 150t. Oh, why did I say our x? We're setting our y equal to 0. And that's this one. Our horizontal distance, we're setting our y equal to 0. And so this is 2 times 150 square root of 3 minus 16t, because I factored the t out of both of those terms. And when you do that, t equals 0, or 150 root 3 minus 16t equals 0. 150 root 3 equals 16t. Divide by 16, divide by 16. And you get a t value of 75 root 3 over 8. And this is seconds. And so now, where your y is 0, you're going to find your x value there. So x of 75 root 3 over 8 gives me approximately 2,435.696 feet. Now the speed of the cannonball, I'm going to do that in a different color. Our R of t was 150 t times I plus 150 root 3 t minus 16t squared times j. And our velocity was 150I plus 150 root 3 minus 32t times j. So to find the speed, we're going to take the square root of, and it's going to be the 150 squared plus the 150 root 3 minus 32 times, and then that's when we're going to put in our 75 root 3 over 8 square, or no, not squared, sorry. Let's extend that. Whole thing squared. I was thinking that that itself was squared, but that whole thing is squared. Which is going to be the square root of so this is and if you put this in your calculator, instead of me writing it over again right here, it miraculously does become 300 feet per second. And you have actually found this, right? The double bar V of 75 root 3 over 8. So that's going to be your speed. Speed of the cannonball at impact. All right.